Hi, ladies and gentlemen. Welcome to iConnect Talks. Today and next Friday's iConnect Talks are special episodes for 2022 Rising Stars of Light. I'm Chen Ziguo, editor of journal Light Science Applications and director of journal eLight. Very nice to be here. Before we started the campaign, please allow me to introduce some history about Rising Stars of Light. So, Rising Stars of Light was initiated in 2018 by Journal Light Science Applications under the directorship of Professor Yuhong Bai from SciAmp, Chinese Academy of Sciences. And since 2020, because of the COVID pandemic, we decided to move it online. So we are very happy to have iConnect as our co-host. So our appreciations also go to Professor Alice Zhang for founding iConnect and supporting Rising Stars of Light. As mentioned before, Rising Stars of Light is bonded with Journal Light Science Applications, which is a leading optics journal covering comprehensive topics in optics. So recently, we have received our latest impact factor of 20.2, which has been the top 3 optics journals for the past 3 years. And it's also great to share that LSI now publishes more than 260 papers per year, which makes us the fastest journal and also the largest volume journal among the top 5 optics journals. So to better serve the community, the same team of Light Science Applications founded 2 sister journals in the past 2 years. One is eLight, which was launched in last June. So with the world's leading scientists as our editorial board members, eLight is started to capture the most breaking and transformative works in optics, which can bring fundamental changes to the field. So launched for only 16 months, eLight has received, eLight's papers have received average size of 29 per paper and 10,000 downloads per paper and also 43 autometrics per paper. So this reflects our quick visibility in the field, and such data is already competitive with the counterpart data of the top 2 optics journals. At the current stage, eLight waives publication fee and also provides incredible author benefits and multi-channel resources to help promote your researches. Another journal is Light Advanced Manufacturing, which was founded in late 2020. The journal focuses on light-based manufacturing and aims to publish the top-notch works in this field. So by far, the journal has published more than 80 papers, 7 printed issues, and also 1 featured issue on holography, which receives popularity and visibility. As a Diamond open access journal, the journal does not charge any fees from readers nor their authors. So this is a good time to submit. And by far, the journal has also been indexed by DOAJ. So ELSA, eLight, and the Liang have co-hosted a series of events, and among which Rising Stars of Light is a particular event to support the most brilliant young scientists in optics worlds. With 2 years offline events and also 3 years online events, if you count this year in, we have attracted sorry, we need to go back to the previous page. Yeah, thank you. So with the 5 years competition, we have received more than 300 nominees application and announced 52 finalists and also 20 winners. And for that, we attracted 0.7 million audiences. And here I'd also like to thank our previous retired committee members. They are Professor Chenupati Jagdish, Professor Jialin Cao, and Professor Hui Cao. And this year, within 2 months, these applications, we have received nominations and applications from top optical institutions from all around the world. And to deliver our condolences and honors to our recently passed away friend, Professor Gabriel Popescu. He's a giant at the field of microscopy and holography. And we decided to name this year's faculty and postdoc track awards after Gabby. Gabby, hope you rest in peace. And after the application, we have come to the first round selection. And with 2 tracks committee, we are able to select a few outstanding young scientists. And here I'd like to thank our committee members for their devoted contribution. Without your help, Rising Stars of Light cannot happen. So based on their grades, 12 finalists, 6 of each track were selected, and they are going to present their talks and competition on today and next Friday. And the 2 sessions is going to be hosted by Professor Qifan Yang from Peking University and also Professor Shuo Sun from UC Boulder. And each finalist is going to present a 15-minute talk followed by 8 minutes question and answers. And right after next Friday's competition, we are going to announce the results and host the award ceremony. Don't miss any of that. So I guess that's basically the information. So I'd like to hand over this session to our first session's moderator, Professor Qifan Yang from Peking University. Qifan, please.
Thanks, Chenzi, and hello, everyone. I'm Qifan Yang from Peking University, and I'm the host of 2022 Rising Stars of Light. This is my 2nd time on this stage, but I still feel very excited because here you can connect to the most talented young scientists and also the broadest audience in the field of optics. For people who have followed this event for years, you may notice that this year we split the tracks for PhD students and for faculties and postdocs. We are very delighted to see that many young scientists have made great accomplishments at a very early stage of their academic career. That is why we decided to open a track for PhD students to share their research and insights of optics to a broader community all over the world. Of course, this event would not be so successful without the long-lasting support from our amazing committee. Now, let's welcome our committee tonight. Professors, so the first is Professor Na Liu from University of Stuttgart, and also Professor Nicholas Fang from University of Hong Kong, and Professor Chaoyang Lu from University of Science and Technology of China. He is also the committee chair. And also Professor Martin Booth from University of Oxford. Professor Booth has a conflict schedule so that he will miss the first talk and join in half an hour. And then is Professor Igor Akhronovich from University of Technology, Sydney. Now let's give the stage to the young stars. They are Andrea Cordaro from AMOLF, Jialin Meng from Fudan University, Hansen Zhong from University of Science and Technology of China, Liang from MIT, Danhao Wang from University of Science and Technology of China, and Geyang Qu from Harbin Institute of Technology. The first speaker tonight is Andrea Cordaro from AMOLF. Andrea, now you can share your slides.
Yeah, I'm sharing it. Do you guys see everything?
Yes. So
okay.
I think now you can start typing and also you can start your presentation right now.
Yes, okay. Thanks for the introduction. In the next 15 minutes, I will give you an overview of our efforts about metasurfaces for analog optical processing. Now, image processing is at the core of some new disruptive technologies, such as augmented reality, autonomous driving, object recognition, and in general, computer vision. And all these applications have in common the fact that they require fast and efficient image processing, so mathematical operations on matrices of pixels. Now, this can be done in an analog fashion already by means of Fourier optics, but this comes with really bulky setups. Or it can be performed digitally by means of algorithms and standard microelectronics. But we're now hitting a severe bottleneck in terms of high power consumption and also speed. So the idea here is actually to outsource some specific tasks whenever possible to analog platforms. So for example, we could envision a metagrading that would recognize input characters and send them to a different direction according to the number that is showing up in the image. Or as I'll show you in a minute, we designed and fabricated a metasurface that actually is capable of performing edge detection on an input image. And this comes with a lot of advantages. And the first is that everything is very compact. It's sub-wavelength in thickness. And so this means that you can integrate it into an existing optical system, for example, without adding thickness. And it's also fast as light propagating through the metasurface and passive. Plus, a lot of information is already in the analog domain. So we can just process it before we even discretize it. Okay, so I will show you quickly three platforms. And the first one is about spatial differentiation. And this is interesting because performing derivatives on an image, it's gonna reveal its edges. And edge detection is in turn a fundamental tool in image processing. So how do we do that? Suppose we have an arbitrary input wave signal and we want to take the second derivative. So we want to have the second derivative in output. Now, the Fourier transform of the output would be minus k squared times the Fourier transform of the input. So what this formula is telling us is that we need to basically modulate the spatial content of an input according to its k vector. If this modulation is parabolic, then we are effectively performing a second order derivative. Okay, so the bottom line here is really that we need to design a k-dependent transmission, T of k, or in other words, the metasurface transfer function. So to do that, we exploit the resonant transmission of this metasurface composed of basically silicon nanowires on top of sapphire. You can see the SEM here. And this has a resonant transmission. This is experimental data where you can see a nice Fano line shape. And this is due to the interference between a broad fabrical background that is given by the fill factor and the thickness of the metasurface, and quasi-guided modes that can be launched along the surface. Now, if we change the angle of incidence, then what's going to happen is that the resonance is going to shift basically following the dispersion of the leaky modes. So we have two important properties basically here. So we have a strong change in transmission due to the Fano line shape, and also a sensitivity on the incoming k vector. So basically, this is actually the ideal platform for us to design a k-dependent transmission, so the transfer function. If we take a crosscut of this plot here, we can basically follow the transmission as a function of the angle. We can plot it out here. And you can see here, we can optimize it to be parabolic. And this depends on the asymmetry of the Fano, on the dispersion of the leaky mode, and on the Q factor of the resonance. So these elements basically completely allows us to design the transfer function at will. And this is all experimental data. But next, we want to basically try if actually we can process images. So we basically first need to prepare an image in input, then project it to the metasurface, and then basically we need to read it out after the operation. So basically what we do here with this setup is that we illuminate an object, we project it to the metasurface with this two objective, and then basically with this, the rest of the microscope, we read it out on the CCD. If the illumination is off resonance, basically the input image, which is for example, our logo or a famous painting, is not changed. But as soon as we hit the resonant wavelength, then you can see that you get only the edges out of the image. So this is basically analog edge detection. Okay, so the second platform. So at this point, our question was basically whether we could actually tune the operation in a dynamical fashion. So, for example, can we switch on and off the edge filtering functionality? And to do that, we combine tungsten disulfide. This is an excitonic material, to a high index grating like the one that I showed you before, and we really combine those in on a chip. So we create a device, and then we squeeze as many devices as we can on a real chip. More specifically, we want to take advantage of the tunability of the transfer function that it's given by the grating, and we combine it with a gated 2D tungsten disulfide monolayer that we can basically switch by carrier injection via gating. And so the trick here is to basically align the Fano resonance from the grating to the excitonic resonance, okay, this wiggle here, such that when we basically quench the exciton, the resonance is going to shift, okay? And this is enough to actually change the transfer function at this specific wavelength here. So we can test this numerically. And then if the exciton is present, then basically not much is happening again to our institute logo. But as soon as we basically quench the exciton, you get quite efficient edge filtering. So this can be switched externally with an electrical signal. I've performed the fabrication and experiment, and this is how the final chip looks like. And if you zoom in to look at one device, this is how it looks at the SCM, and this would be an optical microscopy image. And if you zoom in even more about here, then you can really see the grating. Now we performed also optical and electrical characterization. You can see here our Fano line chip. And if you also zoom in this section, you can actually basically see the exciton resonance. And if we switch the gate voltage to inject electrons in the layer, you can basically quench the resonance and also shift the Fano. Now, it's a small modulation, but for us was an important first step towards the goal. All right, so the last platform is about integral equations, and those are equations of Fredholm equation of the second kind. And this is basically an equation where the unknown function g is inside and also outside the integral. This function k, it's called kernel, and it's known. And this is also a known function, it's called the input function. Now, to start building the analogy with this platform here, which is a metasurface coupled to a semi-transparent mirror, we start by discretizing the equation and recast it into a matrix equation. So the variables u and v become vectors, and the kernel is basically discretized into a matrix. So the analogy with this platform here is that basically also here we have discrete channel, and each channel, basically each input port corresponds to a sampling point in on the unknown function. Also, the scattering matrix of the metasurface is basically mapped to the kernel, okay, which is now a discretized matrix. Okay, so we still have to solve this equation. We just recasted it into a matrix form, and to do that, we use a successive approximation. So we start with G naught, that's and we set it equal to the input function, and basically this corresponds to a situation where we have a set of plane waves addressing the system from the input ports. Now, what we do is that we take this G naught and we plug it back into the first equation to get a more refined guess, G1, okay? And this is basically corresponds to a situation where light has interacted once with the matter surface. If we now plug back again G1 to the first equation, we get an even more refined guess. So, and light has interacted twice with the grating, and so on and so forth. So you see that we start building a series in powers of the scattering matrix, and this is called Neumann series. Okay, so the solution is actually the infinite sum, and it's equal to the inverse of the identity matrix minus scattering matrix times the input function. So to recap, this mapping is basically based on three ingredients. So first, we discretize the system, and we set the dimensionality of the system by setting the periodicity of the metasurface, and hence the number of diffraction grating. And we map the kernel to the metasurface scattering matrix. And finally, we need to have a feedback system that basically would perform the Neumann series, okay, in an analog fashion. And for that, we have a semi-transparent mirror. So the first question is, okay, but can we actually design a metagrating given a desired scattering matrix? And to do that, we use a joint method-based topology optimization. And we end up with this weird unit cell composed of silicon and silica. And basically, the figure of merit for this is the distance on the complex plane between the desired scattering parameters and the optimized one. And actually, you can see that we can get pretty close. And we can also get very close to the ideal contour in fabrication. So this is an SEM of the metasurface. And here you have an SEM just of the unit cell that it's overlaid to the ideal contour, and you can get you can see that we get extremely close. The last ingredient is the feedback system. So we basically put down the mirror. You can see a feedback cross section here, and we basically read out the solution in transmission. Okay, and basically we measure the transmission from each input channel to each output channel, and we compare it with simulation. As you can see here, compares very well for all the scattering parameters in transmission. And from this information, we were able to actually reconstruct the solution provided by the metasurface experimentally, including experimental error for three different input function, and in real and imaginary part. And as you can see, actually, the trend matches rather well. Okay, so with that, I would like to conclude. And also I want to thank all my collaborators of the last 4 years. Thank you.
Thank you, Andrea. It's a very nice talk. So now let's give the stage to the committee members. So you are free to ask questions in 8 minutes. So professors, when you want to ask questions, please physically raise your hands. Yes, Professor Fang, please ask question.
Okay, thank you. So I noticed that you were using we throughout your presentations. I just wanted to seek your clarification on what do you describe as your own unique contribution to the work that you are presenting?
Yeah, thanks. So I've actually done from the theory and the design and the fabrication and the experiment. So all the stuff that I've shown, I've performed fabrication measurements and design. But obviously, you also work with other people to understand the ideas or to come up with the new ideas. So yeah, but I've done all of this basically. Can you still hear me?
Hi, Professor Liu, please.
Yes, very nice talk. I got a question regarding your active part, and then you commented on the slide that there was kind of very small change. Do you have any plan or idea how you are going to enhance it?
Yes, that's a very nice question. So we are working on it. The main idea at the moment is to basically cool down the system. And basically, this is going to reduce the line width of the exciton a lot. And also, this is going to increase the modulation depth. There's a paper from Misha Lukin's group that actually demonstrated an 80% modulation in reflectance but at 4 Kelvin. So we're also trying to go to that direction.
Okay, thank you.
Thanks.
Hi, Professor.
Hi. Can I ask what are the possible applications you can envision at the moment?
Yeah, so thanks a lot. So basically, any image recognition routine, even if you do it with neural networks, starts with edge filtering. And so basically the idea is that if you can already acquire the image already with just the edges, that sort of like speeds up the entire computation by a little bit. But if you have to do it all the time, this can sort of like sum up. So this is definitely the closest application to reality. And this is useful for basically a lot of stuff in cell phone cameras. Even autofocusing is based on edge detection. And again, any image recognition, really.
Yes, Professor Fang.
So as a follow-up, it's my understanding that image-based differentiation has a long history. And you describe your approach as more power efficient. How much improvement are you envisioning through the method you proposed compared to the existing methods that are already available?
Okay, thanks for the question. This is very interesting. So, so a lot of this stuff has been done in the 60s, and also it can be done with just standard image filtering. So if you retrieve the Fourier plane, you can basically manipulate the Fourier plane, and you can do in a much simpler way image processing. Now, the point is that this basically requires like at least 2 lenses that should be at least 2 focal distances apart. And so this is a lot of space, especially when you try to squeeze it in for example, phone cameras or like real application where the footprint is an issue. So I think actually the main advantage is the footprint, that basically you can just slide in the metasurface in an existing imaging system, and this doesn't really add any extra thickness. In terms of power consumption, I don't have like a real figure of merit, because this also depends on the algorithm that you use digitally, obviously. But let's say for sure, it's also a dramatic speed up in terms of computation, because you need to compare it to light just traveling through a very thin optical system. And also doesn't scale up with the number of pixels, which is also an advantage, because it's not even discretizes into pixel already. Yeah, so that's the main advantages, I would say.
Hi, Andrea. I have my own self has a question. So when you are describing your metasurfaces, so I noticed that is it possible to respond to more colors? Since if you are really want to process a real image, right, it must be colorful. So how do you make this work?
Yeah, okay, that's also a very interesting question. So it's possible to design, for example, even 3 different metasurfaces and stack them. The only thing is that you have to make sure that the transfer function of each metasurface only works at the design wavelength. And then at the other wavelengths, it's sort of like a flat response in K-space. Otherwise, you start basically messing up with the other wavelength. But so you can do multiplexing. Ideally, with inverse design, you can even do it in one single metasurface. Maybe the design is a little more challenging, but it's definitely possible even with the a more simpler final resonance.
Okay.
But it needs design. It needs design. So.
Yes, for sure. Okay, let's thank Andrea Cordaro, and now let's move to our next speaker. Yeah.
Right.
Our next speaker is
Liang
Liang from MIT, and yes, we can see you are sharing now. So if you're prepared, then let's start right now. Okay.
Yeah, great. Okay, thank you for the introduction and for the opportunity to give me this chance to present my work. So in this talk, I will discuss how I use machine learning and computer graphics to improve 3D computer-generated holography. So holography is a method of creating interference fringes for controlling wave distribution in 3D. So here is a hologram modulate acoustic waves to create forces that hold water droplets in the air. If we reduce acoustic waves to visible lights and create millions of such dots, a hologram begins to function like a 3D image that can provide perspective changes. This makes it a promising technology for the next generation near-eye display to enable a true 3D viewing experience. You also notice that holography enables two diverse applications under the same principle of operation. Such versatility makes it a powerful tool in many domains. Here I show three popular applications in medical and life science. And here are some other applications in manufacturing, security, and visualization, the last of which I will focus on today. So to begin with, one can make an optical hologram by interferencing a C-modulated beam and a reference beam on a photographic plate and replace the virtual object using the same reference beam. Computer-generated holography, or CGH, digitizes the above process to create dynamic hologram videos. A typical process involves modeling a 3D scene, turning it into a digital representation, for example, here an RGB plus depth image, and integrating some holograms, typically Fresnel plates emitted by every scene point at the hologram plane. The final CGH is usually a complex valued image by the nature of wave. And with great potential, CGH faces several long-lasting challenges that make it still a futuristic technology. Here I list three major challenges, and my PhD works make efforts towards addressing them by leveraging computer graphics and machine learning. Now I will go through each one by one. So first, the diffraction simulation has a high computational cost, square to the hologram resolution times square to the sub-hologram resolution, the later of which is usually beyond hundreds, and the whole process often takes tens of seconds to complete for just one frame, even on high-end GPUs. There are many approximation methods proposed to accelerate the computation, but they largely trade image quality for runtime comparing to the full computational results. Recently, deep learning has revolutionized the performance of many optical imaging tasks. For CGH, I made a key observation that diffraction simulation is fundamentally a spatially varying large kernel convolution operation, and that can be accurately approximated by a cascade of spatially invariant small kernel convolution in a neural network. And this reduces runtime complexity by an order of magnitude and can further enjoy the speed up from highly optimized deep learning libraries and acceleration chips. Moreover, nonlinear activation layers in CNN such as ReLU can also selectively pass sub-hologram information, making CNN also an ideal candidate for modeling real-world phenomena like occlusion, which I will detail later. So recognizing CNN's benefits, I introduced the first large-scale 3D hologram dataset containing 4,000 RGBD images and paired holograms. I carefully designed the dataset to have high scene complexity and also uniform depth maps to make it ideal for hologram synthesis. Using this dataset, I trained a memory compact residual network that maps directly from RGBD image to a 3D hologram. Notably, the CNN is less than 0.7 megabytes, which makes it easily stored and run on mobile devices. So CNN closely reproduces the phase and amplitude of the target with a PSNR beyond 36 dB and an SSIM of 0.97 out of 1. While largely maintaining the image quality, the CNN gained more than 100 times speed up over the physical simulation and achieving real-time speed on a consumer GPU. Its capacity can also be flexibly configured to balance image quality and runtime. So here is a 3D holographic video computed and captured in real time on a single GPU. The focus is set on the bunny's eye and the background is properly defocused. Real-time results at this image quality was the first of this kind at the time of publication. This is a refocusing video we co-presented. So here we refocus the camera by rotating the focusing lens. And you can see objects at different distance come in and out of focus. This is another challenging test, the same containing characters, numbers, and test patterns. We managed to achieve high contrast 3D projection with no speckle artifacts. We also first time show interactive 3D hologram generation on mobile devices. On the left, we also show how the runtime speed progresses at Moore's law on the past generation of iPhones, which promises real-time mobile computation in the near future. So next, let's discuss challenges in modeling phenomena like occlusion and aberration. So when applying naive diffraction simulation, each point emits a spherical wave without accounting for the 3D scene layout. Thus, wavefront that should be occluded by the foreground, such as the ones carried by the two yellow rays, will still contribute to the hologram. This causes the background light leakage artifacts shown on the right. One of my works introduces occlusion-aware processing by reconstructing the surface geometry and detecting ray-surface intersection, and then selectively passes some holograms and eliminate these leakage artifacts. However, there remain some artifacts of attenuated background at the occlusion boundaries. This is because the commonly used RGB depth image representation for 3D modeling doesn't provide scene points behind the front visible surface, which also contribute to the hologram through diffraction. Because of that, we explore more advanced graphics representations to provide a more complete scene information. Specifically, we look at light fields and layered depth images. So a light field is a 2D array of images that capture the appearance of the same scene from a grid of spatial locations. The visibility of different rays emitted from the same scene point is captured by different cameras, allowing consideration of partially occluded background objects. One of my works shows that using conventional light field rendering for hologram synthesis results in significant information loss and aliasing. We review the optimal rendering configuration, which requires offsetting and reorienting the camera against the hologram plane. When applying this method to realistic 3D scenes, background attenuation and occlusion boundaries is effectively eliminated with a partial occlusion information. In a more theoretical work, we mathematically connect light field with its phase-based counterpart, the Wigner distribution function. This allows us to explicitly define the target angular profiles at different spatial locations and using iterative optimization to obtain phase-only holograms with the prescribed view-dependent effects. While light field is powerful, it is time-consuming and data-intensive to render hundreds of views for real-time applications. So we look at a more efficient representation called layer depth images, or LDI. LDI assumes the ray penetrates through the scene and records every hit to the termination depth as a multi-layer RGBD image. It saves occluded background information in a pixel-aligned manner, which eases inclusion of their partial wavefront. We show for complex things such as this tree example, the LDI can have many active pixels in deep layers. However, if we compute holograms using the first n layers and calculate the difference to the full LDI computed hologram, the sixth layer and after contributes less than 0.07% of total energy due to successive occlusion by the previous layers. Thus, we can omit them for practical applications, while rendering a 5-layer LDI can be easily achieved in real time and data efficiently on a single consumer GPU. The LDI can similarly eliminate the background attenuation artifacts, and by learning from LDI plus hologram dataset, a CNN can also accurately model this multi-layer occlusion process with high fidelity. One challenge of using LDI as a universal representation is data capture in real world, since physical rays cannot penetrate the object. Nevertheless, we show that by just feeding the RGBD image to the CNN, but forcing it to predict the LDI computed hologram, we can implicitly teach the CNN to jointly estimate the occluded background and incorporate their wavefront contribution to the hologram calculation. The resulting CNN can produce realistic occlusion boundaries very similar to a full LDI computed hologram, but without the actual need of an LDI. A direct benefit is now we can directly take a cell phone captured RGBD video and turn it into a visually pleasant 3D hologram video with no occlusion artifacts as we captured and presented here. This will be highly useful for generating AR/VR content from commonly available mobile devices. Another phenomenon we model is abrasion correction. Hologram quality often suffers from imperfect optics and varies on users' vision conditions. The left video shows an uncorrected grid hologram under aberration and mouse-tracked real-time aberration correction using Zernike polynomials. By covering the system aberration in this example, astigmatism, and creating a user-specific data set, we show that we can train a CNN to perform hologram synthesis and aberration correction at the same time. In this experimental result, a focus is set on the leaves, and the uncorrected hologram exhibit horizontally dominated blur from the astigmatism, and CNN hologram successfully eliminates it. So that concludes the discussion for the second challenge. And lastly, let's look at reliable phase-only conversion. So existing spatial light modulators may only modulate phase or amplitude. For holography, phase modulation is preferred. So we have to convert or directly find a phase-only representation for the intrinsically complex hologram. Two typical approaches are iterative optimization and double phase encoding. Without going into details, the former method is more time-consuming but may give better results. The later method is very fast, but not always working well for different target 3D scenes. For example, in this detail-rich scene, the standard double-phase method produces strong speckle artifacts. If we zoom in, we may see aliasing patterns in rapid phase-changing areas, as shown in the bottom left. It can be shown that for double-phase holograms, the noise intensity peaks in high frequency, while signal intensity peaks in low frequency. Using this observation, we show applying low-pass filtering to complex hologram before double-phase encoding removes the aliasing and results in speckle-free 3D hologram. Yet a disadvantage of this approach is we have to manually scan the optimal filtering parameters to incur a minimal loss of resolution while suppressing all speckles. As shown above, the best parameters vary across scenes, and if we cannot find them automatically, this method won't be suitable for real-time applications. So to address that, we introduced the first hybrid training method that combines supervised and unsupervised learning to synthesize phase-only hologram end-to-end. In supervised training, the complex hologram prediction is directly supervised by the target hologram. In unsupervised training, the prediction is propagated to the hologram plane, goes through a lightweight filtering CNN, which replaces previously manually designed and optimized filter, and finally gets double phase encoded. Notice that the optimal filter hologram is unknown. However, we can simulate the reconstructed focal stack from the phase-only hologram and minimize the difference to target focal stack to indirectly supervise the training for the second stage. So using this method, the end-to-end generated hologram produces artifact-free 3D images for different scenes and better preserves image resolution, at which simple low-pass filtering produces severe speckle noise. The benefits come from the filtering CNN, which learns to perform content-adaptive local filtering to minimize unnecessary blurs at low-frequency regions, while strengthening filters at high-frequency regions. This result ends my technical discussion, and as a quick summary, I present several works that innovate the full pipeline of CGH generation, from more data-efficient but information-rich representations, to deep learning-based wave simulation surrogate that can also jointly perform background estimation, aberration correction, and finally, hybrid training methods that enables end-to-end phase-only encoding. They jointly assembled a machine learning system that powers real-time holographic 3D displays at unprecedented image quality. So that concludes my talk for today, and thank the committee for your attention. I'm now happy to take questions.
Thanks, Liang. Very nice talk and excellent time control. So now let's leave the questions to the committee members. Hi, Professor Liu.
Yes, maybe I start. Very beautiful talk. So I have a very fundamental question. Can your concept also be used for acoustic holography? So I have a colleague here who does really also fantastic work along this line. And then due to the different nature of acoustic waves and optical waves, what could one modify to adopt your concept in acoustic holography?
Yeah, I think it's definitely applicable to acoustic holography. I think the principal operation, as I mentioned earlier, are basically the same. It's just the wavelengths are different, and the interference fringes are much more visible, as shown in the first page of my slides. So I think the forward model is similar, so we can also generate data sets and train neural networks. I think we have to be cautious about, say, the loss functions, which might be different as to visual images, but I believe there should be, targeted loss functions for acoustic holograms. So overall, I think there is no big problems of applying this whole pipeline, translating this whole pipeline to acoustic holograms. And I'll be happy to chat more about the detailed applications, and maybe we can figure out what will be the best functions and best loss functions and best network structures for translating the application. Yeah.
Mm-hmm. Thank you.
Sure.
Yes, Professor Lu.
I'm very impressed by your beautiful talk and also the very powerful technology. Can you tell us a little bit more about what is your next step along this line of research?
Yeah, I have several interests. So one of the challenges in holography, I think in recent years, many challenges have been solved in the software side, but on the hardware side, people have done analysis, and also in one of my papers, I did analysis. If we want to achieve a large field of view near-eye display using holography, we need a very high resolution spatial light modulators. I'm talking about a scale of, say, 10K by 10K, spatial light modulator. And this can be quite challenging. So one way we are looking at is how we can increase the display attendu on the space bandwidth product using a low resolution SLM, but adding a static passive high resolution components like a high resolution phase mask, which will increase the diffraction angles. And we can jointly optimize the hologram and this static phase masks to increase the display attendu while not increasing the resolution of the active device. So I'm thinking about, creating a data set of this jointly optimized phase device and also the hologram, and then see if machine learning methods can also accelerate the generation of this particular type of holograms. So that's one thing on the hardware side. And on the software side, another challenge people recently discovered is because holography uses the principle of wave direction, and the induced blur is also coherent blurs, which can have these fringe effects. Well, in real world, the blur is much more incoherent, where the sunlight and also the natural light is incoherent. So one thing I'm looking at recently is how we can force this coherent model to produce more towards incoherent blurs, which will be really beneficial if when we are creating an AR device and you are going to overlay the projected 3D images into the real world. when you focus at that particular real-world objects, if the projected object is defocused, you want the defocus blur to look similar to how the real-world object defocus. And another challenge we are looking at is existing setups require filtering of higher order diffractions because of the grading structure of the spatial light modulator. And this filtering usually requires a full F system or Fourier filter, which will greatly expand the system, will make the system very bulky. So one way we are looking at is if we can directly modeling this higher order diffractions into our imaging models, so that instead of discarding them, we can leverage them to create our images. Maybe this will increase the dynamic range, but also preserve the image quality. So that will help reducing the display size significantly. So that's a few directions we are exploring, and I think all of those directions are quite exciting. Yeah. Sure.
Yes, Igor.
I have a question about your software. Obviously, there is a lot of work going into analyzing and predicting these images. I wanted to ask about the packages. So is that something that you write or you adopted from a more traditional image recognition patterns? Can you tell us a little bit about how do you develop this machine learning and the training of the neural networks?
Yeah, so first, our code are all available online. So if you visit our web project page, you can see the code released on GitHub. We also released the data set. As I mentioned in the talk, main purpose is to provide a data set so that people can better investigate machine learning algorithm and systems. And back to your question, so I didn't really adopt any existing code base because most of the code base are not differentiable, so we cannot train machine learning systems. So we wrote a in-house whole pipeline using TensorFlow so that we can directly leverage modern machine learning packages. And then we also design our own renderers to create all the images, whether light field or RGBD images or layer depth images. We wrote all of them ourselves so that we can have the precise control of the scene, the layout, and also the distribution of, say, the rendered objects and also their depth distributions.
Okay, so time for the Q&A session is over, and thank you, Liang, again. Now let's move to our next speaker, Jialin Meng from Fudan University. Jialin, you can start sharing your screen.
Okay, thank you. Okay, hello everyone. I'm Jialin Meng, a PhD student in the School of Microelectronics, Fudan University. Today, my speech topic is Integrated Sensing Memory Computing Neuromorphic Device based on Optical Simulation. I will give my presentation in 3 aspects, including research background, research contents, and conclusion and prospects. Firstly, I will introduce my research background briefly. In the era of artificial intelligence, speed and power consumption have become 2 major challenges for computing, and there is an urgent need to develop new brain-like storage and computing integrated devices for the post-Moore era. The human brain has approximately 10 to the 11th power neurons with 10 to the 15th power interconnecting synapses, through which information processing and storage can be realized simultaneously and efficiently. Inspired by the human brain, artificial neural networks have emerged a surge of development in recent years, owing to their capacity to achieve massively parallel, efficient energy utilization, flexible adaptation, and to accelerate event-driven computations. However, the bottleneck is that most of present synaptic devices only have pure electrical modulation that are still subject to a number of significant challenges, such as the isolation of neuromorphic computing and data acquisition. It is noted that approximately 80% of the information humans obtain from the environment is through our eyes. Therefore, the implementation of optical modulation would bridge the gap between visual system and the human brain. The integration of efficient optoelectronic modulation is crucial for neuromorphic systems applications, such as artificial eyes and supervision. In another aspect, the alliance of photonic and electric operation in one hardware synapse enables the realization of comprehensive and complicated synaptic behaviors, including heterosynaptic plasticity and synaptic adaptations. In our work, the efficient integration of sensing, memory, and computing of optical information in one device unit is really realized. Then is my research contents. We constructed a high-speed optoelectronic multi-level memory device for neuromorphic computing, which could achieve 6 speeds under pulse widths of 50 nanoseconds. Compared to the state-of-art memories from the aspects of response time and data storage level numbers, this device has much faster operation time and more storage states than other non-volatile memories. The development of memory devices with logic function is of great value for the improvement of computing efficiency and has important guiding significance for the development of in-memory computing. Taking A and B as electrical and optical stimulus respectively, the different stimulus of the input are controlled to realize logical AND and logical OR regulation. Then we utilized the multi-bit memory to realize optoelectronic neuromorphic behaviors with ultra-low power consumption of 0.58 femtojoule per spec, which is 5 orders of magnitude lower than the biological level of 100 femtojoule per spec. Moreover, the memory device also could realize the simulations of synaptic behaviors with optical and electrical modulations synergistically, such as EPSC, LTP, LTD, and etc. The photoelectric dual-modulated memory device can provide a novel way for the future memory devices in big data era. This is the schematic of optical and electrical pulses used in our experiments. The device could realize heterosynaptic plasticity modulation under optoelectronic additive and subtractive co-modulation. Through optoelectronic co-modulation, the device could increase the weight modulation range to 203%, which greatly increased the modulation degree of the synaptic device. Furthermore, we utilized the optoelectronic properties of the device to conduct Pavlov's dog experiment successfully. In our case, light pulses function as food, unconditioned stimulus to activate salivation, which is considered as an unconditioned response. And the voltage spikes were taken as the Bell conditioned stimulus to stimulate a conditioned response. After the training by light and the voltage spikes, the current of device could induce to the level above the salivation threshold 1 nanoampere. And it is the first time that the photoelectric dual-modulated Pavlovian dog experiment and the learning, forgetting, relearning rules combined and verified by our artificial heterosynapse, which is important to the fast learning due to the less training was needed for repetitive learning. Taking advantage of the excellent optoelectronic properties, we fabricated an environment-adapted artificial retina device and realized the function of sensing memory computing of information in one device. This is a schematic diagram of biological visual system. The biological visual perception system consists of retina to receive and pre-treat the light information and optical nerve to transduce the optical information, and also has the brain has visual cortex to process and memory information. The first figure in this page is the optical mechanism of device. Under optical stimuli, a number of photo-excited electron-hole pairs would generate in the channel. The long-lived electrons in conduction band could induce Li ions in ionic layer drift toward the direction of aluminium oxide layer. At the interface of aluminium oxide and Li ions are partly intercalated into aluminium oxide layer, thus decreasing the effective oxide thickness and thus increasing the channel current. These are the conductive behaviors of device by optical test, including EPSC, PPF, LTP, and etc. We know the level of light intensity can be varied from a fraction of lux to more than 10 to the 4th power lux. In order to avoid the injury from irritating light, the optical sensitive size of retina can adapt to light through self-regulation in the visual system, which named light adaptation. Similar response to the light intensity could be realized with our device. When exposed to dazzling light, biological eyes can adjust the pupil size to control the incoming light flux and regulate the optical sensitive neurons of retina to adapt to the hard light. Similarly, our artificial retina could learn to adapt to the strong light stimuli through a modulatory synapse. By introducing negative voltage pulses, the current could fall down below the threshold. Besides, the capacities of pre-processing and recognizing images were simulated successfully by the artificial retina perception device based on the optoelectronic modulation. Artificial retina system array was constructed for image noise preprocessing, and artificial neural network was for image recognition. This is the detailed process of image recognition by optoelectronic artificial retina device. It can be seen from the figures. Recognition rate and efficiency were both improved after ARI's preprocessing. The last part is conclusions and prospects. Our work is from constructing optoelectronic memory to optoelectronic neuromorphic computing, and then to optoelectronic artificial retina device. The integration of efficient optoelectronic properties may provide prospective applications of optical information in artificial intelligence development. That is my report. Thanks for listening.
Thank you, Jialin. Very nice talk. So now let's get back to the stage. And oh, Professor Martin Booth, you're back. So Martin, if you have any questions, please raise your hand, and then you are free to ask questions. So now let's start the Q&A session. Hi, Professor Fang.
Yeah, so very nice talk. I really enjoyed listening. I just wanted to seek your input on how do you compare your proposed artificial retina versus the existing ones. And I think you also mentioned about event camera, right? How would you compare in terms of the original idea or key performance?
Okay, our artificial retina device, it is really realized the large information sensing and computing and memory in one device. It avoids the information, computing, and memory to transfer. In other reports, the information sensing and information processing is usually separated, so it will cause the efficiency, the high efficiency. But our work integrated the sensing, memory, and computing in one device, so it has more efficient working.
Yes, Igor.
Thank you for the nice presentation. Can I please ask about the 2D material device where you had a layer of MOSC2, I believe? Can you explain why did you select that particular geometry or that particular material?
I chose the two-dimensional 木流烯as our channel material because it has excellent photo response. So we choose it as our channel material. Yes.
And if I can follow up, how large are your devices? Are they 10 microns? Are they millimeters? Are they 1 micron? What's the lateral footprint?
You mean our device, the size of our device?
Yes.
Oh, okay. The size of our device is at macron level, about 2 micrometer. Yes.
Yes, Martin.
So thank you for the talk. In the later slide, you suggest about having this as part of an artificial retina. I understand that is it correct that the device performs some part of the computation, but you would also have an additional neural network behind it? Is that correct?
Sorry, can you repeat it again?
I understand that part of the computation is done in the actual optical or the optoelectronic device, but I think you suggested that behind that, there would be a neural network processing as well. Is that right?
The artificial neural network is conducted on computer. It's a simulation.
Okay, so does that mean that part of the computation is done in the device and part of the computation would be done in the computer?
Yes.
So, okay, thank you for confirming that. My question therefore is, what is the benefit of having some of that computation in the device rather than simply having a detector array followed by a computational neural network?
In fact, we are now exploring to construct a real array to realize the artificial neural network. But now the two-dimensional materials is hard to make large area array, So it is really a challenge, but we are now working on it.
Mm-hmm. Okay.
Yes.
Yes, Laura.
Yes, I got one question. I was wondering about the fidelity of your device, for example, that artificial retina, because it encounters the charge carrier separation. And then, or I could ask, what is the typical lifetime of your device?
The lifetime of my device.
Yes, so how robust is your device in general?
I don't know whether I can answer you. This is our rotation and the cycle test. You can see from the figure, it has 10 to the 4th power second and has the 100 cycles test. And it is still very stable and very stable performance.
Okay, thank you.
Oh, thank you.
So we have time for a final question. So myself has a final question for Jialin. So you are expressing that the opportunity of making artificial retina. So I would wonder, so how many pixels you are expecting in the future that this device is capable of integrate? And also, do you expect the size of each unit to be smaller so as to be more identical to the real kind of the cells in our eyes?
And in our artificial retina system, it consists of 64 pixels, but it is conducted on computer, not a real retina array. Yeah, and we now have no some comparison between our retina device with the real human eyes. But I think this is a good suggestion. Maybe we can explore it in the future work.
Okay, thanks, Jialin.
Oh, thank you.
So now let's welcome our next speaker, Hansen Zhong from University of Science and Technology of China. Hansen, now you are okay to share your screen.
Oh, okay. Yes. Can you hear me?
Yes. Now you can start.
Oh, okay. Thank you for your introduction. I am Hansen Zhong from University of Science and Technology of China. The topic of my talk is the photonic quantum information and quantum computational advantage. Recently, Speck, Klaus, and Zeilinger were awarded the Nobel Prize in Physics for the experiments with entangled photons establishing the violation of Bell inequalities and pioneering quantum information science. My works during the PhD are focused on the entanglement photons and quantum information. During my PhD, I have finished the first quantum computational advantage, the first photonic quantum advantage experiment, the first demonstration of 12 photon entanglement, and the first demonstration of high-dimensional quantum teleportation. Next, I would like to introduce these works. At first, the 12 photon entanglement experiment. To date, it is also the highest number of entangled photons. In this work, we have developed frequency uncorrelated SPDC sources and design a high quality entanglement source. This is the first near perfect SPDC entanglement source satisfying high entanglement fidelity, high collection efficiency, and high indistinguishability simultaneously. And this is our measure data. And all these features are satisfied simultaneously. And this is our experimental setup. We have performed a 12 photon entanglement experiment to generate a 12 photon GHZ state with a fidelity exceeds the threshold of 0.5, 3 times of standard deviation. And this is the first work that we have demonstrated the 12 photon entanglement. And then I would like to introduce the high-dimensional quantum teleportation experiment. In the past, after the first quantum teleportation experiment, in the past more than 20 years, there are lots of quantum teleportation experiments, and especially in 2015, there is an experiment demonstrates that quantum teleportation of multiple degree of freedom. However, all these experiments are teleporting qubits, which is a subspace of the real system. Therefore, to pursue the dream that teleporting a real system, it is necessary to demonstrate a high-dimensional teleportation. And then to implement the high-dimensional quantum teleportation, we have to implement the high-dimensional Bell state measurement, and similar to the standard Bell state measurement of the qubits, that is a beam splitter in the optical circuit. We can implement the 3-dimensional Bell state measurement as a quantum Fourier transformation, and then we design an optical circuit to implement the high-dimensional quantum teleportation and demonstrate the first high-dimensional teleportation experiment. To validate the teleportation, we have measured the experiment data in the mutually unbiased basis, and we verify that our experiment exceeds the classical limit, which means the upper bound of arbitrary classical protocol, and we exceed the Q-trade limit, which means that the maximum overlap between 3-dimensional Bell state and arbitrary qubit. It means that we have demonstrated a genuine high-dimensional quantum teleportation. And next, I would like to introduce the first demonstration of photonic quantum advantage, which is also the most important work during my PhD. The quantum computational advantage experiment is a computational analog of Bell experiments. By demonstrating a stronger than classical correlation, the Bell experiment refutes all the EPR local hidden variable model. And if we can demonstrate an experiment that faster than any classical computer, and then if the task is can only be finished by the experiment, but cannot be finished by the classical computer, then we can refute all the extended Characterization thesis, which says that any physically realizable system can be efficiently simulated on Turing machine. And after the decades of development, the quantum technology are developed to the boundary of the classical simulatable. However, there is still need a long-term development to implement useful error-corrected quantum computing. And the most recent milestone is the quantum advantage, which means that we implement a quantum experiment that can finish some certain tasks that classical computers cannot finish it. In 2019, the Google realized the first quantum advantage experiment with superconducting QPs. And there are, after the experiment, there are many theoretical development to challenge the Google's quantum advantage. And now it is believed that the Google's quantum advantage are no longer established. And the quantum advantage experiment is not a one-shot experiment, but it should be a long-term competition between the quantum and classical. And the classical theory need to improve it is need to improve the theory of calculation, and in experiment, it is need to improve the experimental technology to close all the loopholes. And here, in this work, we are focusing on the boson sampling. The boson sampling is with a fixed number of input photons, and then we sample the output distribution of photons. The output distribution of the photons is extremely difficult. To classically calculate the distribution requires exponentially times. And however, after years of development, today the state-of-the-art standard boson sampling are still 20 photons. However, a quantum advantage experiment requires more than 50 photons. Therefore, we move to the Gaussian boson sampling. Gaussian boson sampling can solve this problem. It is because that with the Gaussian boson sampling, we can make full use of the photons and no longer restrict our quantum source in the low gain regime, and we can generate many photons simultaneously. And the Gaussian boson sampling, the output distribution is a summation of all the possible passes, but also summation of all the possible photon numbers. It is also an extremely difficult task that requires exponentially times. And it is our experiment setup. It is our photon source of the setup. We designed a frequency uncorrelated quantum source and design a stimulated parametric down conversion source. And then all the photons are fed into a scalable ultra high efficiency interferometer. It is a 100 mode interferometer, and in the upgraded version, it is 144 modes. And all of the input photons are phase locked. We design an active phase locking to control to feedback the fluctuation. And it is an overview of our upgraded version of the quantum advantage experiment. In this experiment, we have observed up to 113 photon events. And validate the quantum advantage is also a difficult task. And to validate the experiment results, we split the experiment results in 3 different regimes. The easy regime, which means that we can obtain the full output distribution of the experiment. And then in the sparse regime, which means that in most of the output pattern, we can only detect 1 event or 0 event, and therefore we can only validate the samples in the sparse regime with some statistical method, such as the Bayesian method or likelihood method. And then in the intractable regime, which means that the photon numbers is more than 40 photons. It cannot calculate the probability of the theoretical probability is also an extremely difficult task, and we cannot validate the experiment data directly, and we can also view the in this work we can view the trend of the validation in the sparse regime, and estimate that our experiment in the intractable regime is also quantum advantage. It's also performed as we expect. And then we benchmark the computing performance. It is the benchmark that the left figure is a benchmark in the Sunway Taihu Light supercomputer, and we estimate that our experiment is 10 to the power of 24 order faster than the supercomputer, and also our experiment is also partially programmable, and now we are developing a fully programmable device.
Hansen, you have 1 minute left.
Okay. Also, there are many applications of the Gaussian boson sampling, such as the molecular vibration or single electron transportation, and so on. And finally, I would like to thank the Professor Jialin Meng and Professor Chaoyang Lu for the guidance, and thank all the colleagues for the help during my PhD. Thank you for your listening. Any questions?
Thanks, Hansen. So the committees are free to ask questions. Yes, Nicholas.
Yeah, very impressive work. Could you please use 1 sentence to summarize the thesis or the key question you are trying to answer in your thesis?
In a summary, can you repeat your question, please?
Right. So what is the scientific question that you are trying to answer in one sentence?
Okay.
Or can you differentiate it from engineering effort?
Okay, thank you. The most important work is that we have demonstrated the first photonic quantum advantage experiment that demonstrates that the quantum device or quantum computing can exceed any classical computers, and it proves that the power of quantum computing. That with quantum computing, we can finish some works that a classical computer cannot do that.
Okay, so Igor, you raise your hand first, so you start.
Yeah, maybe I will continue on Nick's question here. Can you maybe explain what was your contribution to the work? Because you showed, I mean, absolutely terrific data, of course, covering, you know, everything from boson sampling to improving performance and down converted sources and others. So what was your contribution to the work?
Okay, thank you for the question. All of this work, all this work I introduced today, I am the first author of all these works, and in this quantum advantage experiment, I have designed the protocol or the setup, and I designed the photon source, the SPDC source, and the stimulated parametric down conversion. And I have also analyzed the experiment data. And of course, with the help of my colleagues.
Okay, maybe Laura first.
Yes, thanks. You mentioned that at the beginning, it was only partially programmable, and then you figured out some scheme which could make phase fully programmable. Because of the time, you did not go into that. Maybe you can say something about it.
Okay, yes. Thank you. That is a great question. In this experiment, I say that the experiment is partially programmable. Is that because we can only programmable the input phases of the input source, and however the interferometer is still unprogram. We cannot programmable the interferometer, and however the fully programmable interferometer is possible, and we are developing the technology to establish a fully programmable interferometer.
Yes. So what is the trick to do that? I did not get it.
The trick is that if we can tune all the phases in the interferometer, in this interferometer, there are many beam splitters between each layer, and if we can program, if all the phases between the splitter, we can. If we tune the phases between all the splitter, then the interferometer is programmable, and we can implement a transformation matrix as we want.
Okay, thank you.
Okay, so last question is for Martin.
Yeah, thank you for the talk. How would you plan to translate this technology from your laboratory into real-world applications? how would you expand it to larger problems, and how would you turn it into something which can be used outside of a lab?
Okay, yes, that's an interesting question and a very important question. That in this experiment, we only demonstrate the quantum advantage, and however, the Gaussian bottom sampling has many applications in the real world, such as we can estimate the spectrum of molecular vibration, or we can estimate the current of a single electron transpilation from the sampling results. There are many theoretical works on it, and if we have a fully programmable experiment, then we can demonstrate this experiment immediately.
So thank you. I think my question was more about this is a very complicated experimental system.
Yeah,
and it's very difficult to align and calibrate and maintain.
Yeah.
So what can be done to make this more translatable to other users?
Okay, thank you. You can see that in this picture, our device is very huge and certainly untransferable. And in the future, I guess that we need to develop the integrated photonics technology that all of the devices are integrated into a chip, and that should be excellent work.
Okay, the time for the Q&A session is over, and thank Hansen again. Now let's welcome our next speaker, Danhao Wang, who is also from University of Science and Technology of China. Danhao, now you are okay to share your slides. Excellent.
Okay. Hello, can you hear me?
Yes.
Okay. Hello everyone. My name is Danhao Wang, and I'm also from University of Science and Technology of China. It's my honor to be here to introduce our research works in USTC. And before I go into the details about my research works, I would like to introduce a little bit about what is the 3-nitride semiconductor. The 3-nitride semiconductor are directly bandgap semiconductor with widely tunable bandgap, and they can be easily doped as N-type and P-type, and could be heteroepitaxy on foreign substrate. Besides, they have excellent thermal conductivity and chemical stability. As you may see, the nitride materials are very powerful materials. And the nitride materials could be also used to construct optoelectronic devices, such as LED, laser, photodetector, and so on. And my research topic is going to further explore the new optoelectronic functionalities and applications of gallium nitride-based materials. Traditionally, we normally use the thin film structure to construct the semiconductor devices. However, when the thin film structure grows on a foreign substrate, it must obey the strict lattice match growth rule, which means there will be lots of dislocation in material. Compared to the thin film, the nanowire structure grown by the molecular beam epitaxy didn't require lattice match, because the strain can be released directly in the growth mode, and we can obtain nearly dislocation-free material. And additionally, their light surface to volume relation means it has high light absorption efficiency and easy to be surface separated. Previously, the gallium nitride nanowires are emerging as superior material candidates for achieving the efficient artificial photosynthesis. And by alternating the gallium from aluminum atoms, the aluminum gallium nitride nanowire should have similar benefits in the PC environment, possibly expanding the applications in solar blind photodetection. And most importantly, those effective approaches in enhancing the visible light PC catalysis could also be applied in the aluminum gallium nitride as well. So based on my previous work on the active site synthesis and identification and the understanding of the interaction, I want to leverage my strengths and start to apply them in the gallium nitride material. We combine the rational design active site with MB-grown gallium nitride nanowires to explore new device functionalities, such as the photoelectrochemical type photodetector applications, which will be discussed in the following slides. So the main timeline of our research is as follows. We firstly demonstrated the algae nanowire-based photoelectrochemical type photodetector, and then explored the bidirectional photocurrent phenomena and the carrier manipulation, and try to explore the novel applications of such devices, such as the optical communication, optical logic gate. Now I will discuss my first work in algae nanowire-based PC devices. So we construct for the first time a solar blind PC-type photodetector based on platinum-decorated P-type algae nanowires and obtain an excellent photodetection performance. The photoelectrochemical type photodetector, which is different from the conventional solid-state photodetector, have many advantages, such as the photolithography-free and low-cost fabrication process, superior tunability, and relatively large photocurrent. Here is the working principle of our devices. When the nanowire is illuminated by the UV light, the photogenerator carrier is excited with the downward surface band bending at the nanowire and electrolyte interface as the driving force. The photogenerated electrons will drift to the surface and participating in the hydrogen evolution reaction. Meanwhile, the band bending inducing holes drifted to the opposite directions to the platinum content electrode and participating in oxygen evolution reaction. And the electrochemical workstation connects corresponding electrical signals. And thereafter, the hydrogen ions diffuse through the electrolyte and reach the working electrode. But this means the whole circuit is completed, eventually realize the solar blind photodetection. In short, the working principle of the photoelectrochemical type photodetector is a combination of semiconductor physics and chemical reactions. And then we characterize the detail of the device. As shown in this figure, or P-type algae nanowire-based PCBD show excellent wavelength selectivity for solar blind photodetection. Meanwhile, the responsivity and the response speed is sensitive to surrounding environment, such as the light intensity, the applied voltages, and the electrolyte concentration. As we know, loading noble metal on the semiconductor has been proved to be an effective strategy to modify the PC performance. Thus, we decorated the P-type algae nanowire with platinum nanoparticles through the photodeposition method, as shown here. And with the proper surface decoration, we achieved high responsivity and fast response speed. We believe that such high performance mainly originates from the high material quality of algae nanowires and fast interfacial kinetics, and as well as the high carrier separation efficiency after the platinum decoration on nanowires. Then next, I will start to introduce the second part. For PN junction, people know that the PN junction provides rectification behavior as building blocks in many electronic devices. As an example, the PN junction can be used to build photodiode, which works based on the classic semiconductor physics. It can capture and convert optical signals into electrical signals, widely used in many fields. But however, owing to the rectification behavior of the PN junction, the current can only flow in one direction in this device at a constant bias, which will possibly limit the functionality of this device. Because the photoelectrochemical type photodetector operates under a combination of semiconductor physics plus the chemical process, which offers us a new degree of freedom to manipulate the carrier transport process in the semiconductor devices. And since we have learned the photoresponse behavior of the N-type and P-type nanowires in PC environment, we're thinking what's going to happen if we combine the P-type and N-type nanowires together to form a PN junction nanowire and apply it in the same device architecture. And in this work, we construct a PN junction-based PC-type photodetector and observed a unique bidirectional photocurrent in the PN Helical junction nanowires. So let me introduce the working principle of a device. Essentially, by illuminating the device at two different wavelengths, we can possibly trigger different redox reaction at the nanowire electrolyte interface and inducing the polarity reversal of the photocurrent. So under the 254 nanometer illumination, both the L GaN and the GaN segment will absorb the light, and with the downward surface band bending at the PL GaN and electrolyte interface as the driving force, the photogenerated electrons will drifted towards the surface and participate in the HEI reaction. And simultaneously, the photogenerated holes from the P-type segment recombine with photogenerated electrons from N-type gallium nitride at the space charge region. And the photogenerated holes in the N-type segment migrate towards the external circuit and participating OER, as exhibiting a negative photocurrent signal. Interesting, under 365 nanometer illumination, only the N-type gallium nitride will absorb light because of their band gap. And with the upward surface band bending at the N-type and electrolyte interface as the driving force, and the photogenerated holes in the N-type gallium nitride will drift towards the surface and undergo the OER reaction. And meanwhile, the band bending and building electrical field of the PN junction pushes photogenerated electrons drifted towards the external circuit and recorded as a positive photocurrent. So, unlike the conventional PN junction photodetectors, the photocurrent of our device is determined by the number of photogenerated carriers that participate in the redox reaction, which means the redox reaction rate should also be considered. With the guidance of the DFT calculation, we found platinum decoration could induce the device with better hydrogen absorption, free energy, and high efficient charge carrier extraction. As shown here, the S-group nanowires show nearly defect-free single crystal structure. And then we use the in situ photodeposition method to selectively deposit platinum nanoparticles on the top of nanowires as shown here, and then construct a corresponding PCA photodetector for performance evaluation. As we can see, after platinum decoration, when device was illuminated with 254 nanometers light and the negative photocurrent appears, thereafter, when the device was exposed to light with longer wavelength, the photocurrent polarity was reversed from negative to positive. Such phenomena provides a fast approach to distinguish the different spectral bands by simply verifying the polarity of the photocurrent, which couldn't be achieved in traditional photodiodes. And since the homogeneous structure is much more suitable to be considered as a reference rather than the top P segment platinum decoration, we construct a new core shell nanowire structure to further reveal the underlying mechanism of the bidirectional photocurrent. We choose the electrodeposit is the amorphous molybdenum sulfide, not the platinum nanoparticles, to combine with the 3 nitride nanowires to obtain the polarity switchable photoconductivity. As you can see here, the amorphous molybdenum sulfide is successfully decorated on the 3 nitride nanowire structure. And so for this device, as I mentioned before, when the PN junction nanowires are illuminated by the 365 nanometer light, only the N-type segment could absorb the photons and participating in the OER reaction and displaying a positive photocurrent. But for 254 nanometer is a little bit different. In our previous work, we found that the two competing charge transfer process at the nanowire surface as well as in the PN junction co-determine the photo response behavior of the device as seen here. And we also found that when the polarity of the photocurrent change from negative to positive, the response time will dramatically decrease by an order of magnitude, which means the dominant process changed. So for bare nanowires under 254 nanometer illumination, since the hydrogen absorption energy of the bare nanowire surface is not suitable for efficient HER, and considering the two competing charge transport process as shown here, and the OER process still dominates the direction of net photocurrent in bare nanowires, resulting in a lower but still positive photocurrent. After we decorated the amorphous molybdenum sulfide, the electrons in the P-type segment could immediately participate in the reaction once they are generated because of the HER performance boost and lead to a net negative photocurrent. And the DFT stimulation results are in line with experiment, confirming the successful absorption energy modification of the nanowires after decoration. And those photo response results undoubtedly prove the excellent tunability of our core shell nanowires for future spectrally distinctive photo detection. Then let me introduce a little bit about the potential applications of such devices. So for potential applications, we demonstrate a prototype of seawater-based PCPD for portable and wireless communications, which can transmit the ARC code as shown here, USTC. And we also demonstrate the prototype of reprogrammable optoelectronic ternary logic gate using PN junction nanowire-based PEC photodetector. So in summary, in my past research, I've been working on the material synthesis and the characterization and the PEC type photodetection and fabrication in gallium nitride nanowires. We can continue to further explore and improve those device performance, meanwhile to explore those device applications in a broader field. For example, in the bio-related applications and imaging and wavelength discrimination and so on. And finally, I would like to thank Professor Hailin Sun and my team in USTC. Without them, I cannot achieve so far. And thank you for your listening.
Thanks, Danhao. Excellent talk. So now the committee members are free to ask questions.
Okay.
Yes, Martin.
Thank you for the very interesting talk. Please, can you tell us more about the applications for these devices? What
applications? Okay. Thank you for your question. That's a very important question because those three works is just a prototype of our devices and published in year 2 years, and the applications we are still trying to figure out what's the advantages of this device compared to the conventional photodetectors. Because the working principle of the device of our device is a combination of physical process and chemical process, which means a new freedom we can obtain compared to the traditional photodetector. And for example, we have the electrolyte environment, which means we can combine the bio-related field with us together. And we also demonstrate a unique bidirectional photocurrent, which is even can't be achieved in the traditional photodetector. And based on this phenomenon, we can explore so many interesting works such as optical communications and the ternary optical logical gates and so on, such like that.
Okay.
Yes, Nicholas.
Yeah, so I think that's a very impressive new material that you described. In terms of efficiency, can you comment on what is external quantum efficiency of your device and what are the limiting factors?
You mean the EQE efficiency? About I think 60% perhaps, and the limit is that the limit of our devices are absolutely 100% because for a device once you generate electrons and holes, it must participate in the chemical reaction. So the EQE couldn't beyond the 100%. It's the limitation because of the working mechanism of our devices.
Just to clarify, I was trying to gauge what is the limiting effect you observe in your experiment. What are the losses associated? What are the losses associated with the limited quantum efficiency?
maybe I think the chemical reaction process maybe, and I think this is the main limit for our device, because electrons drifted in the semiconductor is much more efficient than in the electrolyte. But at the same time, the electron also provides us so many opportunities. So so that's it.
Yes, Laura.
Yes, thank you for the talk. I try to understand the role of your PT particles. Did you try to integrate a Schottky contact in combination with your semiconductor device?
You mean the platinum decoration, right? Or actually, we didn't figure out if it's Schottky contact or ohmic contact, because in the field in PC community, we normally think it's a nanoparticle on the huge semiconductor surface, and we normally use the DFT calculations to verify the structure, the dot structure of the semiconductor and the platinum at semiconductor system. It's quite a bit different from the traditional semiconductor community, but people are still, discuss about if it's ohmic contact or Schottky contact of the platinum nanoparticles on the semiconductor. But there were lots of work talking about that. It still need to further to figure it out.
But then, how is your energy band modified due to the presence of PT particles, in terms of the work function that you have introduced over there?
I think in the after the platinum decoration, the band structure of the mixed system is actually different from the bare nanowires, and which could help us to to separate the photogeneous carriers. You can see in my DFT calculation results and other PC papers.
Okay.
So we have time for one more question. Yes, Igor.
Thank you for the presentation. Just maybe a quick clarification. So don't you etch and remove the nanowires when you're doing your detection or this photoelectrochemical processes? The material
No. Actually, we use the molten beam epitaxy to directly grow our nanowires on the silicon platform. So we just need to, to make the ohmic contact on the backside of the silicon and, packaging them and then directly to test the device performance. That's it.
Okay, so if no more questions, let's thank our speaker again. And now let's move to our next speaker. Yeah, our final speaker of tonight is Geyang Qu from Harbin Institute of Technology.
Hi, can you see my screen?
Yes.
Okay, hi, so I start. Hi everyone, I'm Geyang Qu from Harbin Institute of Technology. It's a great honor to have the chance to share my research with you. So before I start, I would like to thank you for your time and attention, since it has been quite a long campaign today. My representation topic is intelligent metasurfaces, from holography to optical computing. So the presentation will be roughly divided into 4 parts. Metasurface is a kind of 2-dimensional artificial material which has the ability to control phase, amplitude, polarization, and many other parameters. It has many applications such as beam deflection and polarization conversion, meta-lens, meta-holography, and optical computing. So my presentation today will start with meta-holography. A basic question here is why we need to use metasurface
to generate hologram. Here's a comparison between the traditional devices, for example, spatial light modulator with Metasurface. It's clearly showing that Metasurface have significant advantages, device size and diffraction efficiency. It also has a large viewing angle, which is important for near-eye display applications. However, the statistic nature of Metasurface and the low image quality of metaholography are still limiting further development. So my first work is trying to surprise the artifacts in the metahologram. There are two typical images. The fingerprint and the logo should have had uniform intensity, but actually don't. Such artifacts do not destroy the images, but also introduce potential danger to the user. The intensity of some hotspots is 3 times larger than the average intensity. If metaholography is used in near-eye displays devices like AR and VR, such random fluctuations may make damage to human eyes. So we came up with the idea to surprise artifacts by lowering the spatial coherence of the light source. We started a cooperation with Professor Hui Tao and Dr. Alazar from Yale University, since they are experts in the speckle-free imaging area. They built a degenerate cavity laser that has tunable spatial coherence, and then we applied the laser to generate hologram images. So the mechanism is as below. When the spatial coherence is high, Metasurface will project the images full of artifacts. By lowering the spatial coherence, many other shifted images will be generated at the same time. Since all these images are incoherent, the average effect will flatten the intensity variation. So the experiment feels well with our prediction for different types of metasurface or different spatial travel algorithms. The artifacts are all well surprised by the laser. With the decreasing of the spatial coherence, the intensity becomes more and more uniform. Compared with other suppression methods, our method has many advantages, such as high energy efficiency, high temporal coherence, and spatial coherence optimization ability, and no pre or post processing needed, and also the rapid decoherence speed. So this work gives attention to the artifact problem in metaholography that has been neglected for a long time. We also give a detailed analysis of the artifacts, but I do not think I have time for that today. So in a word, a universe solution is achieved with the help of a degenerate cavity laser. As I mentioned above, another limitation of the metahologram is the statistical nature of the metasurface. This is a long-standing problem, and there are already many excellent works trying to break this limit. Some of them rely on the phase change material, and some of them rely on the multiplexing. Another promising way is the combination of the liquid crystal and the metasurface. It combines the electronic controllability of liquid crystal and the optical properties of the metasurface. I also did some works on this reconfigurable metasurface. One of them is finished with the collaboration with Dr. Wen Hongyang in our group. We designed the parameters of nanotenors carefully until the response has strong dependence to the reflection index of the surrounding medium. By changing the medium from air to DMSO, we achieved 5 types of metasurface with different functions. For example, type 1 metasurface can achieve an off-on switch for the green light, while type 2 metasurface can achieve an on-off switch. Using these 5 types of metasurface, the switching is decoupled to the working wavelength. So we can change the hologram images arbitrarily by changing the surrounding medium. The experiment results fit well with our prediction. Metasurface projects totally different hologram images under different surrounding media. In air, a beautiful fur is doing magic to the green leaves, and in DMSO, the flower shows up and butterflies fly around the flower. Since the metasurface works in reflection mode, the struck color pattern are also demonstrated in the same metasurface. What's more, the holography and struck color can be changed in time with the help of the microfluid channel. So this work realized the dynamic bifunction metasurface. But however, the multiplexing channel number is only 2, which is maybe still much smaller than the traditional devices. So after that, we continue to explore if it is possible to include more functions into a single metasurface. So we revisit the basic diffraction formulas and realize that the usual modulation matrix could be divided into 2 parts, one for the incident light and one for the metasurface. The total modulation matrix can be changed almost arbitrarily by keeping the metasurface unchanged. So following this idea, we demonstrated a reprogrammable meta-holography. The project image changes continually and eventually forms the periodic table of the elements. The proposed idea can also be used for optical correction. Neither the incident light nor the metasurface alone can reconstruct the encrypted image. Only when the incident light and the metasurface matches with each other, the correct images can be shown. So this work demonstrated a new idea for reprogrammable metasurface. Also, the reconfigurable ability actually comes from the modulation of the incident light, but it still shows a possible solution. To be honest, how to realize a real reprogrammable metasurface, especially for visible light, is still a very challenging problem. So during my PhD career, I keep wondering if there's a common way to design metasurface that no need for expert experience, that everybody can do that. So a possible way is to seek help to artificial intelligence. The AI, or specifically seeing deep learning, can turn the complicated problem into simple mathematical models, which is convenient for design novel optical devices. And also on the contrary, on the opposite, the optical devices itself can also be used as a computing hardware instead of traditional electronic computers. So here's a demonstration of using deep learning methods to design metasurfaces. The goal is to generate high-order LG modes with high purity, and which is very important for detection and communication. And there are also some excellent works about it. So the difficulty here is that generating high purity LG mode requires amplitude and phase modulation at the same time. A direct way is using a double layer structure, which means one for amplitude modulation and one for phase modulation. Well, please keep in mind that we also want high energy efficiency, so we only use nanotuners with nearly unity transmission. So the question now is how to design this, two-layer structure. Deep learning offers us a powerful tool, automatic diffraction calculation. So we can design the double layer metasurface using the gradient descent method, which is a real typical method. So as a result, a high order LG mode is generated with nearly 100% purity in simulation, and also our experiment verified the simulation results. Well, as I mentioned above, metasurface not only benefits from AI, but can also help the computing process. A classical example is the diffraction deep neural network developed by Professor Occlusion in 2019. It means using the multi-layer diffraction elements to accomplish the computing process. Since the linear nature of the diffraction elements, we believe that the most suitable scenes for diffraction deep neural networks are for edge devices, which means simple and frequently used devices. And it turns out that the computing system should be simple, but also powerful. So we push the framework to the limit, which contains only one single metasurface, but has comparable performance to the more complicated frameworks. For example, for handwritten digits, the metasurface works as a feature extractor. It extracts the most important features to the input digits, and then a simple electronic layer dumps these features and gives the final recognized result. Almost more than 99% of the calculation is finished in the optical process. Since our framework is very simple, the random error is reduced to the minimum, and as a result, we achieve the record high recognition accuracy of minutes in the experiment. So this work shows the special relationship between metasurface and AI. Not only does the AI benefit from AI, not only does the metasurface benefit from AI, but it can also help the development of AI, such as computing. So here's the summary of my presentation today. I started with meta-holography and make some efforts on reconfigurable meta-holography with few artifacts. Then I explore the unique combination of metasurface and AI. They can help each other to a higher level. Well, in the future, I will continue my research in this, cross-cutting area. And that's my speech. I'm Geyang Qu. Thanks for your attention.
Thank you so much, Geyang. Excellent talk. Yeah. So now our committee members are free to ask questions. Yes, Martin.
Thank you for your interesting talk. So you mentioned at the end the interesting application of using these metasurfaces as part of an optical neural network. Now, one important aspect of a neural network is that it has some kind of nonlinear activation in there. So is there any way in which your metasurface creates that? Where would the nonlinear aspects come into this?
Do you mean that what is the role of the metasurface for neural networks?
Well, my question is that an important aspect of a neural network function is that it has some form of nonlinear process, some nonlinear activation function. So my question is there any way that can be done with the metasurface, or is this done separately in computation?
The neural networks for metasurface is actually a little bit different from the traditional neural network. Neural networks is called diffraction neural networks. So I think it can do some of the work as the traditional neural networks do, but not all of them. It's still quite limited.
So is it really a neural network then?
Well, it has trainable neurons in the phase or the amplitude of at each pixel. Also, it has a multi-layer structure. But you're right, there's a key point missing since there's no nonlinear activation functions for now. So that's also a very interesting topic. So if you ask it is or it is not a neural network, I believe to say it's a very simple kind of neural networks.
Okay, thank you.
Yeah, thank you.
Yes, Nick.
Yeah, very impressive results. I wanted to ask you, what do you regard as the most challenging issue for your field of research? What kind of problem will keep you awake in midnight?
Okay. Since I have done many things, as you can see, so I can just see 2 points. For the first one, I'm most interested now is optical computing, and the most difficult problem puzzle me the night is the lack of nonlinear activation functions. So I think I'm always thinking how to introduce this to the diffraction deep neural networks right now. And there's another way, since for the two-layer metasurface, the key point here is not the design, it's about the fabrication. So it's since the gap layer and alignment is very difficult. So although I don't do fabrication, but I just keep thinking how to do it properly. Yeah, thanks.
Yes, Laura, please.
It's just a general question. So if one starts with a structured light already, then why would I want to put metasurface in between to make different holograms? I could have used the structured light, for example, from spatial light modulator already. Why would I bother?
Yeah, I got the point. Right now we realize, the modulation of the incident light by SLM, but in the future it can be replaced by other equipment like the combination of liquid crystal and metasurface. So also it's not only about reprogrammable metasurface, it's also about optical encryption. If we see we fabricate many metasurface and deliver it to every family, and when they get a signal, they can use the metasurface to decrypt the information. So it has actually two aspects. So I see your point. It's not
But I could do this also with spatial light modulator directly already, but we can talk about it. Yeah.
Yeah, that's an interesting question actually.
So following Laura's question, so I would like to ask a question. So, so there are several ways to construct optical neural networks. So if you need to use metasurfaces, you have to put them layer by layer, kind of manually aligning all these metasurfaces, right? But if we chose many other approaches, maybe we can just implement them on a chip. So how do you compare these different approaches and also discuss the potential of your metasurfaces in the neural network?
Yeah, actually, the neural network on chip is a really, really interesting topic, since it is integrated and the alignment is very simple. But there's also some drawbacks since the loss. So I talked with some experts for silicon crystal. So they are worried about this, since if you got to realize neural networks on chip, the loss is going to be huge. And there's another advantage for free space, so that's what I do now, that it can deal with the 2D image directly. If you want to do a 2D image on chip, you need to first flatten it to a vector. So that also needs actual computing.
Thanks. So if there are no more questions, let's thank our speaker, Geyang, again.
Thank you.
So the oral presentation session of today is over. And before the end of today, we would like to invite the committee to briefly say something to these young scientists, as well as how you feel about these events. So can we go back to the slides that all the committee members can come back to the stage? Yes. So maybe let's start from Laura. Do you want to say something to these speakers today, as all the young scientists who may be watching this event right now?
Okay, it's always very difficult to be the first to say something, but I have participated several events organized by Light. I have to say I was very, very impressed, not only about the students themselves, but also really this kind of organization capacity of Light. So because I'm also working as editor for other journals. So I have to say that then after this, I really need to think about how our journals should do better just to keep up with this kind of pace. And back to the candidates. So what I want to say is, if I look back, when I was young, I don't think I could have done this well. So really congratulations to all the candidates, and you have done really remarkable work today. I was very, very impressed. Congratulations.
Thanks, Laura. So we also hope that we can see more events like this to be hosted by many journals and more broader areas. So next, Nick, do you want to say something to these speakers?
Certainly, I would like to extend my praise to the organizer as well as to the finalists today for your excellent talk and impressive achievements. I think Light has really done an excellent job in promoting the science of optics and photonics, and it can be clearly reflected by the quality and the breadth of the talks that we hear today. And I want to also take this opportunity to bring the challenges to all the finalists of today's presentation, and to think about 5 to 10 years down the road, what you will consider as the most exciting and challenging problems that you want to pursue, using Light as a tool or as your baseline knowledge base. Thank you.
Thanks, Nick. I believe not only the speakers, but also ourselves can benefit from your advice. So next, let's ask Professor Jialin Meng. So as a chair, would you want to say something to the speakers? Okay, I believe there's maybe some internet connection issues. So let's wait a while and let's move to Martin first. Hi, Martin.
Hi, thank you very much. Yes, and thank you to all of the speakers. It's been a very amazing round of a range of different topics, all in very important and exciting areas of optics and photonics. And it's been a real pleasure to be able to review this material and to listen to the talks. I think I'd like to sort of follow on a little bit from what Laura said. Sometimes I talk to my colleagues, so colleagues who are a similar generation to me after competitions like this, and we point out to each other and we all agree that had we been transported from the similar career stage into these competitions, we would have had no chance, because the standards have increased so much in the last approximately 20 years. They've gone so much higher. Not just, of course, the science has moved on, but the quality of presentations and the depth to which people are doing the work is much higher than when I was at that stage. Okay, and so it really is very impressive to see how these things go on. How so many excellent students and earlier career researchers are able to do such cutting edge and impressive work. So it's been a great pleasure to take part in this, and I look forward to doing more in the future. Thank you.
Thank you, Martin. And Igor?
Yeah, so I would like, of course, to congratulate all the young scientists. I mean, you all did an absolutely terrific job, especially coming back of what was a rather tough 2 years. It was amazing to see that you all actually persisted and found the energy to continue your work, and not only continue, to actually excel and publish in top journals, and really presentations were top notch. So really congratulate you. I would like to really congratulate you all with this massive achievement. Of course, Light, I mean, this idea of getting young scientists and now spreading it all the way from PhDs to postdocs to early career researchers, it's quite a nice thing to do. I mean, I think you are very unique, and it's a niche, and I think you kind of opened up a legacy here, really, across all the scientific publishing hubs. So do continue, and the organization is, of course, flawless, and well done for bringing us all I mean, I'm now in Sydney and it's after 1 a.m. and I think for some it's morning and for some it's middle of the day. So I think the commitment is here, and I would really like to see this adventure continues all the way to the years to come. So thank you to Light and the organizers as well.
Thank you, Igor. And following Igor, we also want to congratulate our all speakers for your impressive work that you presented today. And also, let's give our sincere appreciation to our committee again. We also want to thank all the audience who are watching today. Please keep in mind that the faculty and the postdoc check will be hosted the same time next week. And also, the award ceremony is scheduled at the end of the event. So the event for today is over, and see you next week.
Hey guys, I'm Light, Science and Applications, a 10-year-old journal. I suppose all my readers are much older than me, so you can also call me Baby Light, LSA. Back in 2012, my sponsors and publisher gave birth to me. A young blood with nothing but courage jumped to the optics world. As an infant, I was deeply attracted to the fascinating universe of optics, so I ran and ran, never tired of running towards the distance and unknown. When I was 3 years old, I got an impact factor of 14.603 and became the top 3 twinkling star in the world. Since that day, this glorious halo has been sticking with me. Along my journey, I was reported by CCTV, NHK, Eureka Alert, Phys.org, and hundreds of media. The spotlight is everywhere, but I knew I could not get lost. I still had a long way to go. So I launched my annual tradition of light conferences to incubate brainstorms. I initiated Rising Stars of Light to breed those brilliant youth. I founded Light Online Talks to pave the way of communication through the COVID. I started Light People to share the insight of our pioneers. Gradually, I became bigger and stronger and reached the first mountain peak in my life. There I shouldered many heavy-weighted researchers. As my journey continues, I began to travel across continents and build up my baby branches in Beijing, Shanghai, London, Paris, Los Angeles, Sydney, Singapore, and Hong Kong. I was also selected by UNESCO's International Year of Light and International Day of Light as a golden partner. Look, they always reach out their warmest arms to welcome your visit. But there is no everlasting happiness. My growth pains arrived along with the fame. I was criticized for publishing too few and too slow. Luckily, what doesn't kill me makes me stronger. After digesting and coping with criticisms, I grew even faster with the help from my editors, authors, reviewers, and readers. Today, I publish the most and fastest among top 5 optics journals. I guess this is my best 10-year-old gift. Since last year, I had 3 infant sister journals, eLight, Light, Advanced Manufacturing, and e-Gastroenterology. With their joined hands, we are devoted to serving the optics community with better, broader, and brighter platforms. We're coming for the jewel research in the optics crown.